Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. In this video, we'll learn about the basics of acoustic waves and how they propagate in one and multiple dimensions. So let's get started. We found in the last video the acoustic wave equation, and we saw that it was a partial differential equation in space and time, x and t, at least in one dimension. The acoustic wave equation was the second partial derivative of x on p is equal to 1 on a constant c that we'll learn more about in this video, multiplied by the second partial derivative in time of acoustic pressure p. Solving this acoustic wave equation is not immediately obvious on the surface, but many researchers and scientists and mathematicians have studied this equation for many years, and it was in 1747 that Jean-Laurent d'Alembert derived what we call the general solution. The general solution of acoustic pressure for the acoustic wave equation in one dimension is the pressure is, as a function of x and t, is function f1 with argument ct minus x plus another function that we'll call f2 with the argument ct plus x. What's important to recognize here are that f1 and f2 are not multiplied by ct plus or minus x. In fact, these are functions that have arguments of ct minus plus x. So in other words, it's similar to how sine of theta is a function with the argument theta. So that's what f1 and f2 are for us here for the acoustic wave equation. So let's gain some insight about this general solution. It's a combination of functions that include arguments ct minus x and ct plus x. So if we look at the wave equation, it only includes second-order partial derivatives. Specifically, there are no first-order derivatives in space or time in the acoustic wave equation. So in time, a first-order derivative would vary in amplitude like so, and the same thing would happen if we had a first-order derivative in space. It's exponential. So decays occur, whether reducing in time or increasing exponentially to plateau in time. This is what first-order derivatives do in equations of motion. But in this case, we have second-order derivatives. This means that the shape of the response of pressure remains unchanged in space and in time. Mathematically, that means that the function argument remains the same. So let's explore what this means for our acoustic wave equation, and let's focus on the function f1 ct minus x. So let's consider f1 in space x. So we'll draw our function here, which is a function of x and t, and at some time it has this following shape that we see here. Let's refer to this as zeta 1 that occurs at x1 t1, specifically at this point. Now, if we allow some time to pass, what is going to happen to our wave? Well, we just said on the prior slide that the shape remains unchanged in time. So that means that the wave propagates, and now that original point, zeta 1, is now positioned at x2 in a following time. So what we have here is that this point in space has propagated delta x, which is equal to x2 minus x1, saying that this is x2, this point being x1, and it has done so in time delta t, which is t2 minus t1. So if this means that the function argument remains the same, that means we have that ct1 minus x1 is equal to ct2 minus x2. Well, the only thing we don't know here is c. So let's solve for c. In the process of doing so, we find that C is x2 minus x1 divided by t2 minus t1. And if we think about the units here, in the top we have meters in the SI units, and in the denominator we have seconds. So C is a speed. Specifically, C is called the phase speed. It's the speed of a constant point of phase. And we see this specifically, the phase being mapped from zeta 1, positioned originally at x1, now going to x2. C is the phase speed. It is the speed of a constant point of phase. So let's look back to the other function, f2, and its relationship to f1. The general solution contained both of these functions. What we find from the prior example is that f1 was a wave to the right. So that wave propagates in time. And if we perform the same routine like we did on the prior slide, we'll find that the function ct plus x is a wave to the left. In other words, the wave originally positioned here will propagate x in the negative x direction in time. So this is the interpretation of our functions f1 and f2. The general solution contains a wave that propagates to the right and a wave that propagates to the left in this one-dimensional sense. How does this relate to our spherical coordinates, which when simplified are limited to only the spherical coordinate in r? We originally found that our general solution solves this wave equation in one dimension, x and time. What about for spherical waves? So in this case, our wave equation is qualitatively very similar regarding the acoustic wave equation in one dimension of x, or space. Is there a relationship then between this wave equation, the prior wave equation, and the general solution? In fact, there is, and we can make a good hypothesis about this. We can hypothesize that a general solution to the spherical wave equation is just like this general solution to the wave equation in only x and t, but now instead of the function on the left being p, the function on the left will presume to be r times p, just in the same way that we originally only had p here in the acoustic wave equation in one dimension x and then in t. So in this case, our general solution in the spherical coordinates will be r times p is equal to one function f1, which is the function of ct, not minus x, but minus r, plus another function f2, which is ct plus r. So if we then divide both sides of this equation by r, that means our general solution of our r and t for acoustic pressure is 1 on r f1 ct minus r plus 1 on r f2 ct plus r. So one thing is important to note here. When we refer to spherical waves, we initially have waves we intuitively have waves that propagate further out from some origin. And this is what we're used to in our day-to-day lives. This is what we have for the function that is shown here. R increases in time. But for the example that is f2 ct plus r, this implies that the waves converge to the origin in time, which also implies that energy increases in time. This is incorrect. It's not physical. So we ignore this solution to the spherical acoustic wave equation in one dimension R as being mathematically correct, but physically unreasonable and not physical. So then let's explore more about this constant C, the phase speed or sound speed. It takes on a variety of terms. The sound speed is computed through a number of techniques. If we assume the fluid is an ideal gas, the most common computation of sound speed that we'll use in this course is C is equal to the ratio of the bulk modulus, which is in units pascals, and the atmospheric density, which is in units kilograms per meter cubed, and then we take the square root of that ratio. The units, if you work out all the math, will still be meters on second. Another common way of computing the sound speed, if you're more familiar with the ideal gas law, is the following equation. C is equal to the square root of the ratio of specific heats, gamma, multiplied by the atmospheric pressure, P sub naught, divided by the atmospheric density. Once again, the units are meters per second if you work this out. Finally, an additional way of computing the sound speed if you know the temperature of the environment is an equality of the sound speed is equal to the sea level sound speed, C naught, which can be found in many reference books, multiplied by the square root of 1 plus the temperature in Celsius degrees divided by 273. Finally, this leads to a unit value of the sound speed or phase speed of meters per second. For fluids, we more often use the equation that's shown here, where the ratio of specific heats is multiplied by the bulk modulus in isothermal conditions for the fluid divided by the fluid atmospheric density. In this course, though, we'll specifically be looking at gases and will likely use one of the equations that's shown in the middle of the slide. So let's learn more about this phase speed or sound speed. In air, the sound speed is around 343 meters per second if the temperature is around 20 degrees centigrade and we're close to sea level. So this is much less than the speed of light, which is approximately 300 million meters per second, to give you a gauge of how much slower sound is on Earth than the speed of light. So the sound speed on Earth changes quite similarly with the temperature change in the atmosphere. So if we look at this plot here of the temperature of the atmosphere, we see that when we're on Earth, temperature at sea level is somewhere on the mean around 16-15 degrees centigrade and reduces significantly at our cruising altitude for aircraft. We're up here cruising. But as you move further out of the atmosphere, you start becoming more exposed to solar radiation, in which case the temperature fluctuates variably based on the specific location you are in our atmosphere in relation to the ozone layer. But this trend generally holds. In other words, the sound speed changes very similarly with the temperature change in the atmosphere. But it holds only until we reach the case where we exit the Earth's atmosphere and the pressure goes to zero. In that case, the sound speed is 0 meters per second, since we say very often that sound doesn't travel in space. And that's because there is no atmospheric pressure upon which waves could propagate by adjacent fluid particle motion. We're going to test out the speed of sound. I'm going to walk all the way back in this area and then explode the balloon using a trusty pocket knife. Since exploding a balloon is a very loud process, I've got earbuds that I'll put in my ears before doing that. But looking at the difference between the visual change of the balloon disappearing and what the camera picks up, we'll be able to approximate the sound speed from my location where the balloon is popped to you at the camera. So let's go. All right, last touch. Literally. You ready? Here we go. So let's analyze the video and audio recording to approximate the sound speed. This video is the 1 second clip happening approximately at the beginning of the balloon pop. The balloon is heard about 1/2 second into this recording. Ba, 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 ba. The blip at the beginning of the video is due to the software use. Let's say that the balloon pops approximately 1/10 of a second into the recording, and that the balloon is heard approximately 4/10 later at 1/2 second into the recording. After further detail on the engineering survey, the distance between the camera and the balloon popping location is approximately 475 feet. So if we take that distance in meters, which is about 140 meters, divided by the time span, so 0.4 seconds, we find that our approximated sound speed is somewhere around 350 meters per second. This agrees with the tabulated sound speed on Earth at approximately 20 degrees Celsius. So let's summarize what we've learned in this video. We've learned that the general solution to the wave equation indicates that waves travel unchanged through space, and they travel at a speed, the phase speed or sound speed, governed by the fluid properties. Spherical waves only travel outward from an origin. Inward traveling waves are non-physical, although they are, of course, an intriguing mathematical solution to the wave equation, and in some cases are an interesting point of research pursuits. That's it for this video. Now that we've learned about the general propagation of acoustic waves, in the next video we'll learn about single frequency or harmonic acoustic waves.